Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Rolang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
It's been difficult to get everyone in the same venue, partly because of time zone issues. As I mentioned the last time we were attempting this, I feel it's sort of symbolic or representative of something that happens kind of culturally. It's really hard to get the theorists in the room with the practitioners, and it's also hard to get the practitioners in the room with the theorists. However, when it comes to grant writing time, the theorists really need to justify their work in terms of the practitioners. And when it comes to shipping and sweating bullets about the correctness of their code, the practitioners really, really want the assurance from the theorists that things are going to work out. We're at that point, I think, where the rubber meets the road. So Pavel, what we had ultimately wanted to talk about was your experience with temporal logic of actions, TLA plus, and sort of what drove you to use it and what your experience was, and then talk about that experience in the context of what we ultimately want to deliver with the behavioral type system for Rolang. So please feel free to speak to your experience with TLA. If you do have materials at all, the people won't be able to see them, but we can put links to those in when we do the post of the pod.
Oh yeah, I could definitely prepare something. So let me tell you my story with like a little bit of fun experience with formal methods. I had absolutely no idea what formal methods are a year ago. No clue whatsoever. I mean, I've been using for fun some dependent type languages, but the term itself was completely vague to me. And then I stumbled upon a presentation that was held on one of the conferences in London 2 years ago. And that presentation was prepared by, what's the lady's name? I think she was called Kathleen Fisher, but I might be mispronouncing her name. Basically, she was talking about this program which was called Hackasm. I also don't know if I'm pronouncing this correctly. This was a sort of founded by DARPA program where they they did a little bit of research whether formal methods can eliminate exploitable bugs. So they, as an army, they had an understanding that things like security, obviously having hardware and both software not being exploitable is, let's say, important for the army. And they were researching whether formal methods would help, and they had tremendous amount of success of starting with I think it was a Boeing's helicopter that was could be driven with pilots or without them, which Boeing was really assured that it's safe and not exploitable, and the researchers were able to hack into it within 1 day, which I found amusing, and then they spent. And that's an interesting part, that they spent 18 months actually teaching Boeing engineers formal methods, while at the same time re-implementing the kernel for this helicopter from the scratch. And within 18 months, they were able to provide software which was completely unhackable. They had a team of white hat hackers who were unable to hack into it, even though they had all the access to like the design, the code itself whatsoever. So for me, that when I listened to it and then I read the paper where they go into a lot of details of how that was designed, for me that was mind-blowing, because spending like almost 15 years in the industry, whenever I try to think about it, I try not to do that because that makes me crazy. Like, we call ourselves software engineers. My parents both are engineers, and they laugh at me. They always say like, "Oh, you're not an engineer. That's like, your industry is far away from being called engineers." And I see in formal methods a little bit of hope. However, there's I strongly feel that our like formal methods community still haven't derived all the terminology that is needed. But I see that formal methods can be defined, and it's not me talking. It's more like people who I listened to or read their blog posts. They talk about it, that formal methods could be divided into two separate groups. One would be formal verification of code, and the other one would be formal verification of design. And while you get better benefits, especially if you know what you're doing with formal verification of code, where you can formally verify that, hey, this method is saying it's going to do this, and I can guarantee that you don't have to look at the implementation. You have a formal guarantee that it's actually going to do that thing. It's tremendous, and it's outstanding, and that I would just love to have a language in which I could, like a mainstream language, in which I could program like that. But that becomes especially problematic if you design things where the business, like people for who you're trying to create software, still are not fully aware of what they really want to have. Like, things are changing each sprint or iteration, whatever you name it. You get different design decisions being changed and all that, and each time re-implementing the action or any formal like proofs can be cumbersome. So that's when you go into that other part where TLA I guess shines, and that's formal verification of system design, where you can talk about the design and talk about properties, talk about invariants in the design that you would like your system to have, but you don't necessarily have to immediately write any code. You can talk about what you would like to achieve, and then you will have a model checker, which you can think of as a brute forcer, that it will just explore the space of all possible states in which the system can be, and it will look for whether all the invariants, whether all the properties hold. With TLA Plus, that is the way TLA Plus works, is that not only you get ability to write invariants in terms of like a first-class logic, but you also have the concepts of temporal logic, when you can talk about things that will happen one after things that will happen in order. You might say, oh, if this thing happens, then that thing must eventually happen. So you can create sentences like that. So you can think of it. When I talk about it, I always give this example. Imagine that you are encountered, like you have to provide a software which will do this really complex thing. So what do you normally do? You maybe have a conversation with your colleagues. You might have it over coffee. Maybe you write some stuff on the whiteboard. You spend some time designing the idea of how this thing's going to work. And then once you guys kind of like, sure, okay, this is what we want to have, then you spend like weeks or even months putting that design into code. It takes some time for the code to mature enough for you to find the first issues and errors with the design. Sometimes the issues are small and are pretty fixable. Sometimes the issues are so fundamental that you have to spend like months or weeks to just re-implementing the foundations of your Plus gives you is this ability to verify that the very first drawings that you did on the whiteboard, that very first like initial guarantees whether this concept that the team had when it was designing it actually holds. But the process of moving this design, this idea from whiteboard to actual code, that TLA plus will not give you those guarantees. It still requires whatever engineering skills we have up our sleeves, going from the design, so the overall high-level concepts of how the software should work, into the code base itself. But as I said, when we design our system, we might fail twice. We might either fail while in the initial design, where our concept of how this thing should work is fundamentally broken, like we missed something, we missed some initial idea. And also the other place where we can encounter problems is we might get issues when going from our design to code, but also the design might be broken. And TLA Plus gives us this guarantees whether our design is good enough. And it obviously can still break. There's always it's just the TLA Plus is just giving us a language for specifying the system, and then gives us a tool that the model checker that understands the language of that specification and can, let's call it, run it, can explore all the possible states in which the system can be and look for issues and look for problems. And that's what we've been doing with TLA Plus a few weeks ago at an RCast project. So I got excited with TLA Plus a few months before that. I play around with it, in the evenings, and I really haven't done anything professionally in it before. But then I was given a ticket. Apparently there was a weird problem within Casper, a sort of like a liveness problem, because at some point node that tried to join the network could sometimes hang while joining. And it was a bizarre error, and after investigating it, when looking at the code, I realized it's just a typical problem of message being dropped and not being delivered, and our code was not robust enough to handle that situation. And I was like, okay, the fix is easy. But then I wonder, how many other issues like that exist in our code, exist in the current protocol that we have when we implement Casper in two scenarios, and one in the Genesis ceremony, and the other one in nodes joining the network. So I thought this would be a fun experiment, one-day experiment, that I would just specify the whole thing in TLA Plus. I underestimated it. I think that was supposed to take less than a day, took a day and a half, but eventually ended up in the almost complete specification of TLA Plus of Casper in TLA Plus when it comes to how protocol in Casper works, how message. So we didn't specify the Casper itself. We didn't specify blocks being added, merges, and all that. It was more about the messages. So originally, when I joined the project, I was part of the com layers team. So this was the issues I was most concerned with. So I was just specifying what kind of messages are being exchanged at which rate, and what are the invariants that we would like them to hold. And the invariants were simple. Nodes, when we instantiate node, it goes through some state changes, especially during the Genesis ceremony, but also during when it joins the network. It goes through some changes, and the states changes, and depending on which state it is in, it will handle incoming messages differently. So I was able to quite easily specify each of the states in which the node can be, and also specify how it handles the incoming messages. And then temporal invariants were simple. I would say things like, once we get a new node, eventually it has to end up in a state called running. The running state is the state that we call the final state in which all nodes have to end up after going through the Genesis ceremony, or after joining an existing network. And it's also, if you look, it's quite rewarding, for me at least it was, that when you look at the specification as it is defined today, and it's available on our GitHub, you will see, and then you look at the specification, especially the parts at the very end where we describe how the node reacts to different messages depending on the state in which it is in. If you've seen the code base, our code base, Scala code base, you can see direct, like this is like direct connection between the specification and the code itself. And if you know just a little bit of TLA plus, you don't have to know every little tiny detail of it. If you just know the basics, you almost read that specification in plain English. You see things like, given this state, given that message, this will happen, and then you have like a few lines of specification telling you what will happen. So yeah, so that's pretty much the whole story. And eventually, that specifying this in TLA plus, we found the bug in which we already knew about. I was able to, before implementing the software, I was first able to quote unquote, fix the bug in the TLA plus specification. And that once that was fixed, then the model checker immediately hit another error, which we were not aware of at that time, but it was in the protocol. That error was in the protocol. So that allows us to apply yet another fix in the specification. And then the whole spec started running correctly, like all the invariants, all the properties were holding, given the model while the model checker was running, and that gave us some sort of guarantees that the protocol that we have right now, as it is right now, actually is correct.
This is really cool stuff. I'm just curious to start learning about TLA because I'm trying to conceptualize how you can search such a large space of possibilities and be able to detect conflicts in runtime and that kind of thing. What's the main reference that you recommend for TLA?
So just to start from the beginning, TLA Plus comes with two different tools. One actually allows you to write some proofs, but the tool that I was using was the model checker, and it's just exploring all the possible states in which the system can be. Which, with any enough complex system, that number of possible states just explodes to almost something like feels like infinity. So yes, you do have to sometimes limit the number of, like, tell model checker to not explore this area anymore. So just to give you an example, let's say you want to model a network layer, and the way you could model the network layer is, for example, to be for every processes that you will model in the specification, it has a incoming queue and outgoing queue. So when you want to send a message, the message arrives in outgoing queue, and when the message is sent over the network, it disappears from that outgoing queue and ends up that message in some other processes incoming queue. And then you can model things like messages being dropped, like, for example, being removed from an outgoing queue and not arriving anywhere. And then obviously nothing limits the size of the queue itself. We can imagine a system that keeps on trying to send messages and they just never pop out from the queue. But when you create a model, so you keep your specification clean, you keep your specification as no limitation, like there are no limitations and there are no issues, but when you create a model, you can actually specify and you can say, you know what, do not explore all the states where the queue is bigger than 5 elements, right? So that means obviously there might be a bug, for example, in your system where your queue reaches 6 elements, right? And then you will never have an ability to find that bug because you explicitly told the model checker, listen, when you're going to have more than 5 elements, then stop exploring. Like, only focus on situations where the queue reaches out 5 elements and that's it. So yes, that you stumble upon those limitations. And when I was running the model checker for Casper protocol, I pretty much had to put those limitations exactly on the queues themselves, so that the system cannot like possibly, send this tremendous amount of messages on the queue, and because that this way the number of states would just explode to infinity, pretty much. As if it comes to resources where you can learn about TLA plus. So when I say TLA plus, different people might say different things, because TLA plus is a specification language that uses some elements from maths, like from set theory, some from logic, but it is a language that I feel is straightforward and clear for functional programmers, because what you write when writing TLA plus, what you write are basically formulas, and there are always formulas that, as an argument, they take two states. They take state in which you are currently in, and a possible next state to which the system can potentially move in the next step. So that always the formula that you write as an argument takes those two states, and the return type of your function or formula is a Boolean value, whether we allow transition from state one to the second state, or we don't allow it. And then there's also you need to provide a formula, like an initial state formula. So a formula that returns initial state. And having only those two formulas, the model checker can just explore all the possible states, because it starts with initial state, and then it's using that second function that only return true or false, and he's saying like, hey, we're in this initial state. Can I move to that next state, let's say B? And the formula says false. And he's like, all right. Can I move to state C? And the formula says true. So then the model checker can actually transition from initial state to the state C. So in its core, this specification language is very declarative, and whenever I'm showing it to functional programmers, they quite quickly grasp the concept. However, people who tend to write software in more imperative style, they tend to struggle sometimes, because whenever they think about states and the state's transition, because what's state? State is just a set of variables with given values for those variables. And whenever they think about state transition, they always think about a variable changing from, variable X changing from 1 to 0. And when they look at that language, it's sometimes, and I think it's an unfortunate decision, that it looks a little bit imperative in its nature. It looks almost like there are assignments in it. So even though the formula itself is returning a Boolean value, true or false, whether I can go from state 1 to state 2, the semantics that were being used, the syntax that was being used, looks a little bit imperative, especially if you come from imperative background. It looks appealing. It looks just like assigning new values to existing variables. But that's not what it is, and people struggle with that. So then some people created a new language called Pascal. Pascal or Calc, I don't remember. It's a language that mimics. It has two different varieties. One mimics a Turbo Pascal. The other mimics a little bit of C syntax. So what those languages, they compile down to TLA plus. Essentially, you write your specification in this Pascal language, and then the system will compile it down to TLA plus. I find this not really nice approach, because they try to use a syntax, that C syntax, that was designed for talking about statements and talking about statements being executed one after the other, where in any language that we currently have, any imperative language, the determinism is basically written in their core. You can have non-deterministic things in it. That would be just crazy. While when we specify things in TLA class, we want to be non-deterministic. We want to say either message will be dropped or it will be delivered. And we don't want to put any constraints when this happened. We only tell, oh, it's either dropped or delivered. That's it. That's all I know. So coming back to the question about resources, there is a very good book, which I actually own. The author is Hailey Wayne, but that book is, I forgot the name of it, but it's really recently published. But it's unfortunately, for me, talking about those higher level languages, those Pascal imperative kind of languages, and they don't really talk much about TLA plus itself. Leslie Lampert wrote a few years ago a book specifying systems, which is still available online, and you can pretty much get it. It's not fully up to date, but the core concepts stay the same. Leslie Lampert tried to write a second edition of this book, but then he said that eventually he learned that people no longer read books, only watch YouTube videos, and he started recording his own little sessions of like tutorials about TLA plus. So, and those, by the way, those videos created by Leslie Lambert are just amazing. They are really hilarious. They are funny at the same time. You learn a lot, and they are created in this fashion, of this manner of 15 minutes. They are no longer than 15 minutes. So even if you're on commute, you can put your headset, and 15 minutes later, you know a little bit more of TLA plus. And Leslie Lampert is a really good teacher. Like you can learn a lot from it. But if you want to go like into hardcore details, then Specifying System is a very good book. There are not that many resources about TLA plus other than papers and that particular two books.
So that was a really nice presentation or discussion of TLA. I really appreciate that. I wanted to point out that we can map all of those notions very nicely onto the row calculus and row lang. So in particular, the notion of state in process calculi in general is a process. A process is a state, and processes transition via the COM rule, right? So they transition from state to state via COM rule. And when that transition happens, then you accumulate a substitution, right? And the substitution maps directly onto your idea that there are some variables with values, right? The substitution is going to say that in the case of the row calculus that was sent, is now bound to some variable in the body of the for comprehension. So that substitution represents that mapping of variables to values. So they all of those ideas, they land and line up exactly with elements in the row calculus. It allows us to transport the ideas of TLA over to the row calculus whole cloth. And that's exactly what the behavioral types for row lang do. But they do it in a different way than TLA because now the formulae become types for row lang programs. So then instead of checking your design, you're actually going to use these TLA-like formulae to check your running code. The code that you deploy can be model checked to see whether or not it satisfies a particular formula. The big gap here, as I think you pointed out on several occasions when we've talked in public, Pavel, is that you have to be the one that bridges or provides the connection between the model that you built and the code that you actually deploy. That lives in your brain as opposed to in any execution artifact. And so that's the advantage of a behavioral type system, is that we can get all of the the goodness of a system like TLA, but instead of on a model that's only loosely connected to deployed code, it becomes directly applicable to deployed code. Does that make sense?
Yeah, but actually, I do have a question about it, because I couldn't. So here's the thing: I couldn't really. I did a little bit of time, spent some time researching about behavioral types. I couldn't find that much information about it on the web. But I found one of the things that I found was like some, I think, old document on surrounding why we want to have RChain, why RChain is needed, and one of the chapters in that document was talking about behavioral types. And that, correct me if I'm wrong, but what I understood from what behavioral types are, they provide this sort of way of writing proofs about software, about your program, your functions, whatever they will deliver. The same way, for example, languages like Daphne allows you to write proofs, but the benefit.
No, it's not about proofs.
It's not about proofs. Okay.
No. So there's but let's go a little deeper, because because that's a really important question, and it raises all kinds of fun and interesting avenues to explore. So first of all, one of the best papers for behavioral types is Louis Cairas's paper, a logic for spatial and behavioral types for the pi calculus. So that is absolutely a gorgeous paper. The information density of that paper, which is one of my favorite measures is perfect, right? So on every page is packed enough information to keep you completely engaged, but not so much that you're drowning. It's a really lovely paper, and I encourage everyone who wants to learn about behavioral types to read that paper. And then having been strongly influenced by that paper and other background material, which I'll talk about, I wrote a paper called Namespace Logic. So if you want to understand how the row calculus is behaviorally typed, that paper, Namespace Logic, which was published in the Trustworthy Computing at ETAPS in 2005, provides that. And then there's an implementation of the core concepts of that paper in a repo called RowCamel under the Lighthouse GitHub account. Yeah, Lighthouse/RowCamel, and you can see that it will in fact allow you. It will do the model checking, at least in part, for a lot of the different kinds of formulae. And then there's also another piece of software called the Spatial Logic Model Checker, and the Spatial Logic Model Checker implements the Cairas's behavioral types for the pi calculus. So in the SLMC, the Spatial Logic Model Checker, you can write down models in a pi-like language, which is very close. You can see the family resemblance to Rowley. And then you can type check them on the basis of the models. And I strongly encourage people to go through those examples. So if you go to the Spatial Logic Model Checker website, they provide a number of fairly convincing examples, starting from really simple things like a gossip protocol. So you have, in that example, you have a network of processes, one of which knows a secret, and they all follow a protocol whereby they communicate, they whisper to each other. And then at the end, you can prove that following this whisper protocol, they all know the secret. You can do more sophisticated things, and I encourage people to play around with it, where you can have them only whisper to parties that have certain properties, like they know a username and a password, or they know some other kind of authentication mechanism. And in that case, only those authorized parties will learn the secret, and those who are not authorized will not learn the secret. So those are properties that you can write down both at the protocol level and at the property level and check that that's the case. And then they do some considerably more sophisticated protocols, in those examples. So again, the spatial logic model checker provides running examples, and then RCaml also provides running examples. What's interesting about this approach as opposed to TLA is TLA has no vision into the structure of programs. The temporal logic of actions is only talking about the evolution of programs. It doesn't talk about how programs are structured. So for example, and this is an example I've given many times, you can write down a formula in the spatial logic or the namespace logic, which represents a notion of single-threadedness. So you can prove structurally that the program is single-threaded, and that's something you can't see with the temporal logic of actions. I don't remember whether TLA is expressive enough to do this, but you can write down deadlock freedom properties in behavioral logic and in
you can do that. You can do that in TLA.
Yeah, exactly. So notice that the two kinds of examples that we've talked about. One is a security property. We want to make sure that information isn't leaked from one group to another. In fact, we can be very, very sophisticated about these kinds of information control flow properties. The example I often give, because it's both relevant and poignant, is you can imagine a doctor coming back from Sierra Leone, having done some volunteer work, and dutifully goes and gets checked to see whether or not they have the disease. I'm sorry, I'm blanking on the name of the disease. They go and get checked, but there's a mistake in the lab, and so they're cleared to go back into the general populace, but in fact they have Ebola. And so once it's discovered that we now have an agent in the general populace in a big city that has Ebola, there's a kind of control flow that you want. You don't want to alert the media before you alert all the major healthcare providers. So first you want the group of major healthcare providers to know that there is a serious risk. After they are all prepped and everyone is apprised of the situation, then you want to alert the media. So being able to prove that information reaches a particular group before it reaches another group is the kind of thing that you can actually write down in these kinds of logics. And then another kind of thing that you can do is not about security or information flow control. You want to be able to write down whether or not the progress is made or whether or not things get stuck. So these kinds of control flow or liveness properties are also things that you can write down in these kinds of logics. And then the nice thing is, in the case of Rolang, these logics are types, and so you just do a type check as a part of your overall development process. And this is important, and I thought about this quite a bit when I was thinking about where's the best place to introduce formal methods in the developer flow. Because what any developer will tell you that the biggest challenge to developing is context switching, right? So if I'm working in a particular tool and I have to go over and work in a different tool, I can lose my concentration or lose the thread. And it's those kinds of interruptions that are the most dangerous in terms of the committing errors. But if programmers are used to a particular write, edit, compile, and that compilation step includes a type check, if they're already, that's a part of their existing flow, you minimize the committing errors. And so that's why it's very natural to place it at that point in the development cycle. But let me widen the discussion, because it's largely been Pavel and myself, because we've got these two mathematicians in the room, and I want to hear their input. I mean, one of the things that I was going to offer is that when you look at the behavioral types from the perspective of the ladle algorithm, which widens this to not just a programming language or toy programming language like the rote calculus, then you can start to see these wider connections. So for example, the formula that picks out single-threadedness in the row calculus or the pi calculus is the same formula that for a monoid picks out primality. It picks out those elements in the monoid which are prime, which I think is super, super cool, right? It says that there's something about primality that is like single-threadedness. And this captures that notion exactly.
R is the multiplication.
Exactly. That's exactly right. It's a pretty cool connection we don't see until we're sort of working at a particular level of generality. But once you establish those kinds of connections, my feeling is that it becomes another tool in the toolbox, and helps make the connection between the theoreticians and the practitioners. So let me just open it up to you guys, Christian and Isaac, and sort of get your feedback on the discussion so far.
Yeah, so I have a question about the TLA Plus, just because I don't have much exposure to it. I did watch a few of the videos, and I have to agree with Pavel that Leslie's videos are pretty hilarious, and he teaches really well, of course. He's been in the field for 40 plus years, and he's obviously knows what he's doing, and he knows how to explain what he's doing. So I would definitely recommend checking those out. And so my question about TLA Plus is, I understand that it's a language for specification, and you're essentially writing in the language of set theory and temporal logic. So you said that there was a way that you ran some models, and I was just wondering how you actually found the particular bugs that you did find in running these models, and like how they actually present themselves, because I feel like that's maybe a disconnect that I have currently.
The bugs that I found, I put the single temporal property on the system. So first of all, I've modeled a concept of a node. And node was nothing else but just few variables. Like one of the variables was the state in which the node can be. I don't know if how much you are familiar with the node transition states, but it pretty much like few states in which node can be. They all end up in this state called running. Essentially, when the node is in state running, you can consider it a healthy running node that now can do all the cool RChain stuff. But you have to get there, and there's a process of how you're getting there, depending if you're right now instantiating a new network, so you're running the Genesis ceremony, or you maybe have a new node that is joining an existing network. But so what I had was basically I put all few of those nodes on an array. So if I have those few nodes on an array, I already have a concept of a network of nodes running on the network. Now I need the nodes to communicate. Okay, how the nodes can communicate? Well, each of the node can have a variable, outgoing messages and incoming messages. So those variables will be queues, and queues can be represented as linked lists, as sequences of where you first in, first out. And so then I need to model a network layer. So now the question is, what does it mean for a message to go from one node to another? So if I'm trying to send a message, I'm putting this outgoing queue, and sending a message is removing that message from outgoing queue on one node and adding it to incoming queue on other node. And that's it. That's the whole specifying the network layer was just that's pretty much it. It's less than 10 lines of TLA specification. There's no additional magic to it. We only define messages transition from one node to another, and we also modeled a concept of messages being dropped. They don't arrive at their destination.
Notice that the process calculi really have this covered in spades, right? The state transition is communication.
Yeah, right. Instead of almost the other way around.
Yeah, I mean, Pavel has to explicitly model that part of the picture, whereas
Right.
for the process calculi, it's built in. It's that notion, and
Mm-hmm.
it's done at a level of abstraction where you could treat that as message passing across a network, or you could treat it as shared memory, right? Well, names can be modeled as memory locations, and now it's communication via shared memory. In fact, all of those styles of communication have a natural representation in the process calculator. So you don't have to model that part of it. And the modal operator with the logic is now directly related to the communication action.
Mm-hmm.
Answering like what kind of bugs were found, like if that modeling of communication layer was more or less understood, then pretty much like as I said at the beginning, there was this concept of a state in which each of the node can be. And obviously there are like state transitions where we go from one state to another, depending on which messages arrive and in what kind of messages and in which state you are currently in. So I've written this simple temporal formula that I said, and this is the language that you can, I'm using specific words which you can find in temporal logic and in TLA plus itself. So I said, eventually, for every node in the network, eventually all statuses for each of the node are equal to running. In other words, eventually all nodes are in state running. And this is a single line formula, and you use quantifiers from logic like for all nodes, for all n in nodes, such that a status of given node equals to running. So I said eventually, meaning eventually over time, this is where I want to be.
Yeah.
And we had 2 bugs in protocol, which so this is pretty much checking the liveness property of our system. I put some basic like in safety properties to check like if things are working correctly, like no weirdness will happen. But I was more concerned with the liveness because that was the initial error that I was assigned to in Jira was the liveness issue. The node was not progressing in the state transition. Mm-hmm. So now I have this liveness properties. I will check that all the nodes eventually should end up running state, and then I run it, and I found actually the first bug, the Jira bug in the protocol itself, which was fixed, and then we found another one which we also fixed.
When you say that you found a bug and then you fixed it, so how exactly do these bugs present themselves to you? Just like as something that's not satisfied that you expect to be satisfied?
So we agree that I specified how nodes interact and how they communicate, how they send messages, right? I also specified a liveness property. I said I want this eventually this thing to happen. I want this to be all the nodes be in this particular state eventually. Mm-hmm. And then I run the model checker. So then I run the model checker and I did something like a very simple environment. I said like things like, oh, there's this. Imagine that there are those 3 nodes which are running, and here's a node which is in state new, where each node joining the existing network starts in the state new, and then I run the model checker, and then the model checker after like few minutes or seconds, I don't remember right now, stopped, and he said temporal property something like broken, or I don't remember exactly the lingo that was being used, but something like temporal property not checked. And then they gave me a counter example. So then they gave me exactly what happened. Cool. And then you can follow, and that's pretty nice because you follow the steps, and that each of the step is the name of the formula that you created. But because you write this next step formula, but you can combine it from sub formulas, and then you can join the formulas with logic or this or that or that or that. So then each state gets its own name. So you almost read it like in plain English: messages being sent, messages being dropped, a node transitions to this state, but you can also get the God's eye view of not only the given node. You understand all the nodes and all their states at each of the step, like how the variables were changing and all that. And especially if like things like temporal formula breaks, you either end up in a stuttering step or they loop and they just never reach whatever was supposed to be reached. And you can see exactly why that happened. And that was a really nice thing to see because it was straightforward to see. I was just going through this counterexample. I was like, okay, he sent this, that's good. He sent that. Then he lost this message. That's not a problem because he'll resend it, and he did resend it. But then he did something crazy, and I'm like, oh, that's actually right. And then I go back to code, and I'm like, oh, that's wrong. And then I fixed it, and it worked.
That's really cool, and totally makes sense too, thinking about it, because of course, how does it check that your formula is not satisfied, right? It finds a counterexample that doesn't satisfy the formula, and then there you go, it's not satisfied. Yeah, so of course they can just give you that counterexample, and then you can trace that execution path, all the state changes from the initial state to that point, and then figure out exactly what went wrong. That's really cool.
And that's exactly notice that that's exactly the kind of feedback that our type checker will be providing to developers.
Mm-hmm.
So the type checker will say, sorry, your code doesn't satisfy the formula, and here's a trace that is the counterexample.
Yeah, that's cool.
Right. And this is just like what happens in Scala today when you fail to pattern match, right? It provides a counterexample. It gives you a data shape that won't pattern match against your case selections.
Yeah, so having something like that on the compile time level, that would be really amazing from the user perspective. And by user, I mean
Yes, exactly. So, I mean, to me, I think this is really the thing that will begin to set us apart. The behavioral types set our chain apart at one level, just because it provides the kind of security that we're going to need at the point where we're running it at 40,000 transactions per second, right? It's like, imagine having these kinds of liveness issues or these security issues and no way to automatically check them. And as a result, you've got these smart contracts, which are the vast majority, the exposure for these kinds of errors, right? There's only a handful of developers that are writing the core protocol, but then there's the entire world of developers we hope will be writing smart contracts. So the exposure to the commitment of these kinds of errors is much, much greater in the smart contracts than it is in the core protocol. Code auditing does not cut it. The DAO contracts were audited, front to back, left to right, top to bottom, and there were still errors. And this is the same with the parity wallet issue, right? So code auditing doesn't cut it, and we have to do something else. And that's what these tools and techniques provide. And if we don't do something else, when we get to this blockchain 2.0 kinds of speeds, where we're running, ceteris paribus with Visa and other, world-class financial systems, then you get an error like this and you're toast, because in a heartbeat, 40,000 transactions per second, in 1 second the network is taken down, and the only way to recover is a hard fork.
If I may add something to it, because right now Greg, you're addressing people who might be already like sold to this idea, like of formal methods and all that, but there will be people may potentially listening to this podcast, and if you follow ideas of people like Uncle Bob or whatever, they will tell you that the only thing you need is discipline and a little bit of tests. And I don't know if you can know that.
Yeah, right.
There's this thing about, and it's really cool, John. Uncle Bob tells tests the same way Smurf say Smurf, like they always do that, right? It's like tests are really good tooling for reaching correctness, but they are not the only tool that we have up our sleeve. And there's also like a very cool example of where they might fail. There was a few years ago, back in the extreme programming area, when they had this wiki page where they were discussing different problems. So each week somebody would show up with a problem, and the idea was to write a set of unit tests that will show that where the error is and potentially how to fix it. And there was a person who came up with this not really that big of a Java program, a simple program that was running few threads, some threads were adding elements to a queue, other elements were removing elements from the queue. And he said there's a bug in this code, and the idea was to write a test that would show it. And so the people tried to do that, and they spent like weeks on it, and some like very well-known people in the industry at that time were reaching to a conclusion that there is no bug in this code is correct. And then this person who showed that challenge said like, listen, no, there is a bug. And then he showed them exactly like a set of execution steps which were deadlocking this program. The program would pretty much deadlock. And he said, like, listen, given that I just told you what the error is, and given you know exactly the set of execution steps that will reach to that deadlock, now could you write me a unit test that will show the error? And the one guy did, and he measured it with like a time clock. He measured it that he spent exactly 16 hours working on a test that when this test was running, it was creating like 20 or 30 something more threads. And this test had to be run 200 times for it to fail with probability of 50%. So, and then specifying with this any like formal tooling gave you like the answer where the issue is. That somebody specified this problem with TLA plus within like 30 minutes and already had an answer what's going on. So I know it was a very long example. What I was trying to sell here is this an idea that, yes, it's really nice that the industry finally grasp this concept that maybe writing tests for your software is not such a bad idea after all. But we shouldn't stop here. It's 90s already happened. We are in 21st century. We should move forward. There are other techniques, other toolings that people should explore, because no matter how cool the behavioral types will be, no matter how amazing RChain and Roland will be, people still have to use that in order to explore those techniques. And I'm just trying to sell this concept: explore different techniques. Just don't stay with a status quo. Look for other ways to make your software more robust.
I never stop looking for ways to make our code more robust, and in particular to make it's not just the tools and technologies. It's also methodology. Like really simple things like don't check in code that doesn't compile. And in this case, if someone were to have the behavioral types, then they would make sure that they never check in that doesn't at least satisfy certain liveness, safety, and security properties, which I think is going to be a huge win. And very importantly, when we're talking about something that's replacing the financial infrastructure, the transactional infrastructure, and we have to have a level of assurance that's beyond the client-based website, where it literally says, don't click the pay now button twice.
Yeah.
You're right. We're talking about a different level of assurance of the quality of the code, which is a requirement in order for these networks to be actually have utility. We did spend quite a bit of time sort of on the mathematical side last time, and I noticed that we're past the top of the hour. So I think this is probably a good stopping point, but I really appreciate everyone taking the time to engage the conversation. I also would like to put in a plug for the next RCast. We'll be talking about an idea that I hope will intrigue people. For those people who have programmed in languages that have a void star or have an ability to typecast in such a way that you lose all typing information, and then to cast back out of that into a situation where you're asserting the type of the object you've got. But we know that this is very, very dangerous, and it leads to all kinds of runtime execution errors unless you're a serious expert. And I want to argue that that's exactly what money provides. So currency provides this ability to turn anything into a value representation and then convert that value representation back into anything. So the idea is you can always assign a a dollar value to a good or a service or some other financial instrument, and then you can always turn around and take that cash that you've got and turn it back into a good or a service or something. And that is in perfect analogy with this sort of lack of type safety. And I want to argue that with the advent of the blockchain and digital currencies, that we can provide a new notion of currency that is type safe, which then changes the trust proposition associated with the notion of currency. So I hope that we can have a good conversation about that. What would be a typed currency? What would it look like? How would it function? And how would it differ from the notion of currency that we've got? So for those people who are following the RCast, please tune in next time for that conversation.